Hello, welcome to Class Time, your daily classroom for CSEC students. You can watch this lesson in real time on Television Jamaica's YouTube channel or One Spot Media. Send in your questions to Television Jamaica's Facebook page at Television Jamaica or Instagram at television_Jamaica or use the hashtag TVJClassTime. We will be continuing where we left off yesterday in CSEC Math with Probability of Simple Events Part 3. I'm Camille Johnson-Borrell.
And I am Tamika Lodge-Fenton. Let us begin. So the objectives for today's lesson are determine experimental and theoretical probabilities of simple events using contingency tables and use the multiplication rule for independent events.
All right, so before we begin, we just want to take a quick recap of what we would have looked at yesterday. So here we're looking at experimental probability. A company that makes light bulbs tests 100 bulbs per batch. They found that on average for every 100 bulbs, 6 are faulty. What is the experimental probability that a bulb is faulty? So here we were told that for every 100 bulbs, 6 are faulty.
Right,
so we knew it would 6
out of the 100.
Out of the 100, because the 100 would have been our total possible
trials.
Outcomes here, yes.
Right.
And when we simplify our 6 out of 100, we would arrive at 3 out of 50.
So the probability for the experimental probability for faulty bulbs out of a batch of 100 is 600th, and simplified, we're factorizing by 2 there, we get 3/50th. So in order to find the experimental probability, we would divide the number of times the event occurs, in this case, the faulty bulbs, by the total number of trials. And in this case, it's 100 bulbs in each batch, so for every 100.
So remember now, the number of times event occurs would have been 6.
Right.
Yes, 6. And the total number of trials would be 100. Right, good. So
let's just recap.
Yes, so same experimental probability of an event or relative frequency is the ratio of the number of outcomes in which a specified event occurs to the total number of trials in an actual experiment. So remember now, this is looking at experimental probability. And the ratio, for those of us who don't remember, is a comparison between quantities. Ratios can be written in different forms. And here we have 3 different ways we can write ratios. 2 to 3.
We can use a colon.
Yes, we can use the word
2. Or we can represent it like a fraction.
Yes, that's good.
Theoretical probability. A bag containing 10 blue marbles, 5 red marbles, and 2 yellow marbles. What is the theoretical probability of getting a red marble? So there is a difference with experimental and theoretical, correct?
Yes.
All right, so let us see. So let us look at some of the information that we have. We know that there are 5 red marbles in the bag, and we know that in total we would have had 17 marbles. So the number of favorable outcomes in this instance would be 5. That means we have 5 red marbles in a bag of 17. So there are a total of 17 marbles, therefore the number of outcomes is 17. Go ahead. So in this particular case, the number of favorable outcomes would be 5, and the number of total outcomes would be 17. So out of the 17 marbles, 5 of them are red. All right, so the probability, the theoretical probability for this event would be 5/17.
Yes, that is indeed correct. Still looking at theoretical probability, this is the ratio of the number of ways the event can occur. So as we stated earlier, favorable outcomes to the number of total outcomes. So unlike experimental, which an experiment is done, the theoretical is not an experiment.
So you had said that theoretical is pretty much the ideal situation.
Yes, it
All
is.
variable being constant, this is what should happen. You have 5 out of the 17 marbles that can come out of the bag being red.
Yes, that is indeed correct. So we're looking at contingency table, and it provides a way of representing data that can facilitate calculating probabilities. One more point to remember and note about contingency table: it helps in determining conditional probabilities quite easily.
Okay.
So here we're looking at independent events.
Okay.
Independent events.
So this would be something new.
Yes.
So we've looked at events, we've looked at probability, and we talk about the probability of an event happening. We talk about experimental probability. We talk about
theoretical probability.
Now, independent events. What would that have to do with?
You know, I'm thinking here, independent doesn't depend.
Stand by itself?
Yes.
Can
so
do its own
events,
thing? Pretty much.
Let's see exactly what we're looking at. So here we have the occurrence of one event has no effect on the probability of the occurrence of another event.
So in simple terms, what you're saying, if you walk across the room, it has nothing to do with me standing up over here.
Nothing at all.
Okay, so your walking is independent of me standing one place.
Yes,
right.
Yes it is. And for those of us who weren't quite sure what we were sharing earlier, if a particular outcome, such as what we stated earlier,
right,
or event in one experiment does not affect the probability of outcomes or events in a second experiment, then the outcomes or events are said to be independent, and we just shared that.
Right.
So one event, event 2, the second event, is not affected by the first event. Good. Yes. And we're going to take a look here at some activities to see
if they're independent or not.
Are they independent or not?
Right.
So you buy a lottery ticket and you win.
That's a good thing right there.
Yes. Then you win again the next week.
You know you're telling lies now.
Does this change the likelihood of winning on the third week, since you are on a roll? So you're on a roll of winning.
Boy, I'm in a lucky streak.
You win the first week.
I'm going to win again.
You win the second week. You think anything happens here, so does this change you winning or not winning?
It doesn't. It's really, I just had 2 good weeks. So it's really by chance. So it's an independent.
You're sure?
It is.
You're positive.
Boy, but I lose every week, so maybe it does have some bearing,
But in this case, you're winning, you're on a roll.
No, it's not.
So you're right, because the second week winning would not have had any impact, any effect on the first event, which was you winning, yes. And as such, wouldn't have any impact on the third one. So this one is in fact
they're
independent.
Right.
Here we go. So we have it here. Event 1, win the first week. Event 2, win the second week. Event 3, you win the third week. However, winning the first 2 weeks in no way
affects the
likelihood of winning the third week. And in other words, they're independent.
All the weeks stand by themselves.
Yes.
Because winning first week doesn't affect the second week either.
And you could even win the first week, win the second week, and then you lose the third week. So they're all independent events.
Most definitely.
Let's take a look at another example here.
In a game of cards, you draw a card from the deck and get an ace. Does this result change the probability of getting an ace on a second draw from the same deck?
So I pull an ace from the card, right? Does it change the probability?
There are some points that you need to know first. And tell me what you need to know about the deck of cards.
How many cards are in a deck?
All right, there you go.
52.
Something like that?
Yes.
How many aces though?
1, 2, 3, 4 aces.
Great. So now that you know that you pull one ace, tell me.
If I pull one ace, that means I would have now decreased the total number of cards in that pack. And I would have also decreased the ace as well.
Very good.
So that means it's not independent.
Exactly.
Because what happens in the second event
is
going to be affected
by what you did.
Pulling the first ace.
Excellent.
So I don't think this one is independent at all.
It's not. It's not.
Let's double check to see if we're on the right track. So event 1, which we shared earlier, first card.
It's an ace.
All right. Event 2.
Second card could be an ace.
Could be an ace.
Could. But does the probability of you getting an ace, that's the question, does the probability of getting an ace in the second pull, is it affected by your first pull?
No.
You sure? Remember,
Yes,
you had 4 aces, you know?
Yes,
man. You had 4 aces to start with. And when you pull your first ace, you would now have 3 aces, right?
Yes.
Hope that's English, that's grammatically right. 3 aces? Yes. Right. So if you now have 3 aces out of pack of now 51
cards,
because you're 1 card less, your probability will change.
And our total outcomes would have changed.
Be different.
Too,
so
yes.
in this case, the events are
not independent.
Good.
Let's test our brain now if we're learning about independent variables. So we're looking at a third one. So we flip a coin and we get heads.
Okay.
Does this result change the probability of rolling a heads again on the second roll? So I flip the coin,
all right.
I get a head. When I get the head now and I flip it again, will it change the probability?
All right, so let us look at the coin. How many sides the coin have?
2.
2 sides.
I have a head and the tail.
When you flip that coin and you get the head, what do you do with the head? You take it off?
No, the head is still there.
So you really haven't changed the coin. So if you to flip the coin again, you still have the same head and tail. So you flipping it the first time, second time, does it affect the coin again?
No, so that means
they are
independent.
Good.
So my second event would not have been affected by
none whatsoever
by my first
by
event.
The probability of your first.
Yes.
Because you got ahead, but it's changed nothing about the coin. So in flipping it again, the probability remains the same. One side is head, one side is tail.
Yes,
all right.
That's right. So we are getting there with independent events, and we're understanding now what independent events are. So let's take a look at this activity here.
All right. Sage is going to the movies. She's going to the movie with her friends, but she's trying to decide what to wear. She has 3 jeans with colors black, blue, and white, and she has 2 blouses with colors pink and red. What is the probability of Sage selecting a black pants and a red blouse to wear to the movies?
All right, so let's think about this now. So Sage is going to the movies. She has 3 jeans.
All right, so let's put those colors.
3 jeans.
She has what she has. She has a black.
She has a black.
She has a blue.
So she has black pants. She
blue
has
pants.
blue pants.
And she has a white pants. Or she have white pants. You know, she could have several, but those are her colors.
Yes, these are her 3 color pants, right?
Then
and
she
for the
has
blouse, no, she has pink blouse.
Pink and red, right.
So she has pink blouse.
And she has a red blouse.
And she has red blouse.
So she have more clothes in her, but she just want to wear these.
Yes, these colors.
That's what she's thinking about for the movie.
All right, so right here now, we're setting out a little table here.
We want to see what's our possible combination of blouse and pants.
Yes. So right here for the first one, we have black pants.
So let's just write, let's abbreviate them. So we have BP, we have blue. Oh,
yes,
BK.
And we have pink blouse.
All right.
And then we have our blue pants.
And pink blouse.
And pink blouse.
And just put pink. And
I want them to know, man, so that if they just join in, they know what we're looking at.
So we have white pants, and that can be combined with a pink blouse.
All right, so we finish off here with our pink blouse. So these are all the combinations of the pink
any one of the pants.
Yes, black pants,
white pants,
blue pants, whichever one. So now we're on to the red blouse.
Excellent. So she can wear the red blouse with the black pants, what is the probability of Sage selecting the black pants and the red blouse? All right.
And she can also wear the blue pants
with the red blouse. Red blouse. And then she can wear the white pants with the red blouse. So the question says, what is the probability of Sage selecting a black pants and a red blouse to wear to the movies? So basically we're asking, if she were to combine her blouse and her pants, how many times, really and truly, you see that combination of the red blouse with the black pants?
But before we even go to how many combinations as it pertains to her with the black pants and the red blouse. Let's take a look at the total combinations here.
Okay.
So right here, when you're looking at it, we're seeing that she has 6 possible outcomes right here.
So
she has
can
6.
combine those 2 blouses with those 3
The
pants 6 different ways.
6 different ways.
So those are 6
possible
different
outcomes, right? But
now, the
here,
favorable one that we're talking about,
yes,
which is the black pants and the red blouse, is, we only see it one time, you sure?
once. So when we look at our table here,
Okay.
we're seeing it once.
Right.
So we're seeing that black pants, pink blouse, blue pants, pink blouse, white pants, pink blouse, black pants, red and red blouse, blue pants, red blouse, white pants, red blouse.
Exactly.
But we need,
We only
black
want to look at
pants.
the probability of a black pants combined with a red blouse.
So what's
and
the
we
favorable
see
outcome?
it is once out of the 6 possible outfits she can choose.
6 possible outcomes she
6.
can choose.
Right.
All right. So hear this now. She can wear anything she wants.
She can.
But we're looking at the probability of her
Choosing
black
black pants
pants
and red blouse.
And then guess what we're looking here too on our table to see? Our black pants, well, all our pants are independent of our blouse.
That's true, because you can combine the pants with anything, with
Yes.
either of the blouse.
Black pants can be worn with anything, it doesn't matter. So
Exactly.
if she wants to wear it with a pink blouse, the pink blouse is
She
independent
definitely
of the
can
black
do that.
blouse. The red blouse is independent of the black pants. So
her
she can
blouse
mix.
selection is independent of her pants selection.
Yes,
So
that
there are
is correct.
2 independent occurrences. All
Yes.
right. All right. Let's
But
see what we're
can
going to
we
do here.
this another way?
We probably can, because math is awesome. Math can
Yes.
simplify.
So we know right here that our probability then. So let me write it. Our
Right.
probability of black pants and red blouse
would be
gives us 1/6.
excellent.
Right? Now let us
What is the
think
probability of
carefully.
wearing a black pants?
What's the probability of wearing a black pant?
How many pants she have again? 3.
3. So she
what's
has
the probability of picking the black
1.
out of?
1 out of the 3. So
Right.
so probability
Probability
of a black pants
yeah, would be
is 1/3.
1/3. Probability of a red blouse.
How many
She has
colors?
2 blouses, and she can choose the red.
You sure it's
once.
2 blouses,
It's
Seja?
2, man. It's 2.
It's 2
blouses.
colors she tell you that she want to wear.
She have pink and red.
Yes.
So it's 1 out of 2. A half.
Half. All right.
Right.
So here we're looking at 2 independent
Events.
variables again. 2
Right. 2 independent occurrences.
Yes.
The
And we
black
have-
pants stands on its own. The red blouse stands on its own.
And we have the probability of both here. So we have the probability of the black pants, probability of the red pants.
So we're combining those 2 occurrences.
Yes. So when we're combining now the probabilities of 2 independent events,
Yes.
the relationship is multiplication. I bet you never know that.
Well, show me. Let me see what you're saying.
So I'm going to show you and then I talk again.
All right,
So
then.
let me show you now. So the probability of wearing the black pants
With the red blouse,
yes,
and the red blouse.
and the red blouse, the relationship between the combination of these probabilities is multiplication.
Right.
So it's going to be 1/3 times
A
half.
half.
Which guess what? It
That
gives
looks
us
like 1/6.
nice.
Look at that.
So tell me if you learned now.
All right, so I'm going to have to look at this a little bit more. I'm going to really have to take some time. But just before I look at the board, we're going to take a quick break and we'll be back with more CSEC math.
Welcome back to class time. So here we would have left off on this activity. Sage is going to the movies with her friends, but she's trying to decide what to wear. She has 3 jeans with colors black, blue, and white, and 2 blouses with colors pink and red. We were looking at the probability of Sage selecting a black pants and red blouse to wear to the movies. So this is where we were before we took a break, and we are just recapping. We are just recapping on our table here. So we would have represented our black pants, blue pants, white pants, as well as our pink
the
blouse.
Combination of
yes, red blouse.
Any of the pants with any of the 2 blouses.
Yes, so this was just our table here to show us and for us to be able to readily see the probability of wearing a black pants and a red blouse, which we would have shared earlier. We're looking at independent events. So we would have arrived at 1/6.
Right.
We were also looking
Before we move into that, the table has some added information which was there, but we didn't total it. So if you look right at the table, there are 3 possible combinations that you can have with
the pink blouse.
And there are also 3 possible combinations with the red. If you look at the black pants can only be worn twice with either a pink or a red blouse. The blue pants the same 2 times. The white can only be worn twice because there's only 2 blouses to choose from.
Yes.
All right. So then we had gone to the fact that we can move on to the next section.
Yes.
All right. So
here we were now looking at how we arrive here at probability of wearing a black pants and red blouse. So if we are not in a situation where we could draw a table then, as how I would have done earlier,
right,
when we're looking at the probability of 2 independent events taking place, the relationship between these probabilities is multiplication. And here we would have seen 1/3, which is the probability of wearing a black pants, a half, which is wearing the probability of wearing a red blouse.
Right.
And when we multiply these 2 probabilities, we arrived at 1/6.
Exactly.
Which means the probability of wearing black pants and red blouse
is
1/6. Yes.
Now, what you mentioned that what if we can't draw the table? Now, what reason could I have not to be able to draw a table?
Maybe what we have working with is too large.
Excellent. So
It's
if the occurrences are way too much and time consuming to draw a table, definitely the multiplication rule is quite efficient in calculating the probability of 2 independent events.
All right.
If they were to come together. All right.
We're here looking at an activity, a second activity. So go ahead, Tamika, with the activity.
In a group of 60 grade 10 students, 20 study history only, 24 study French only, and 8 study both history and French. Are the events students study Are the events students study history and
a student who studies French independent. So we're looking at 2 events here. A student who studies history and a student who studies French.
Are they
to look
independent?
if these 2 events are independent. So here we're representing this one on a Venn diagram.
Okay.
For us to see what is happening. So this is our Venn diagram.
So the group is 60 students.
60
That's our
students.
universal group. All right, 60 grade 10 students, right? That's
and
fine.
we have history.
20
does
history only.
We have
24
for French
only. And 8 studies both history and French.
Good. So here we know that the probability of a student studying history and French would have been 8. Here we have it.
8 out of
our 60 students.
Right.
So this probability here would be the same as representing it as H. I'm using H for history and F for French. So I'm sure we remember this from sets.
Oh, yes.
So H intersect
French. History intersect French.
Yes, is 8 out of 60 students.
Right.
Which is the same as saying the students who study history and French is 8 out of 60.
Right.
All right. Now, remember now we were looking before if the events
Of a student studying French
and a student studying history, if they are independent. So let's see if we can check if they are independent. So let's look at this number of students studying history. So here we have the probability of studying history. So we have 20 out of 60. What about the probability of a student studying French only? So we have 24 out of 60. So here we have history only.
Yes.
And we have
French only.
French only.
Right.
When we simplify our history only,
we have 1/3.
We have 1/3. When we simplify our French only, we have, so that's, you're not helping
that's
me?
12/30th, so that's 6 into that goes 2,
So it's 2.
15th. 15th. Yeah. All right. So that's the probability.
2/5, not 15, 2/5. Right, so 2/5. So we used 12 as our factor here, so it's 2 and 5, so it's 2/5. So we have this working with. So history only, the probability of a student studying history only, 1/3. The probability of a student studying French only, 2/5. So now remember, if the events are independent, when we multiply them, we're going to see what's taking place here. So let's multiply them now. So it would have been 1/3 multiplied by 2/5, which gives us 2 out of 15. All right. Let's see if we can simplify our intersect here now. So can we simplify this? Yes, we can simplify it and we would arrive at 2 out of 15. So here we have our H intersect VF here to say
so
history and French. So the probability of history and French
being 2/15,
which is 2/15, yes, is equal to the probability of history only,
which is
we're going to leave it as H. So let me, so it would be 1/3 times the probability of French
F.
only, and I'm using F, which is 2/5. So tell me if you think it's correct. So here we have same intersect.
The calculation is correct. Right, so we have 1/3 multiplied by 2/5 gives us 2/15, and it is pretty much exactly what the Venn diagram would have shown, that the intersection with history and French is 2/15.
Yes, so we can arrive now at a little conclusion.
Right, we can come up with a way to
when we're looking at
all independent events.
When we're looking at probability, so the probability of H and F, history and French, is equal to the probability of history, which was history only, multiplied by the probability
of French only. Right.
So here we have our multiplication coming in, which we would have shared earlier, that the relationship between the probabilities of two independent variables is multiplication. And we would have proven it here with our Venn diagram. So we would have looked at what history and French were to be 8 out of our 60, and when simplified we have 2 out of 15s, and here we have our, we would have simplified it here to arrive at our multiplication rule here. So we're on a ball.
So your Venn diagram supports the multiplication rule of independent events being calculated by multiplying the occurrence of one event, the probability of the occurrence of one event, by the probability of the occurrence of the second event. It will give you the probability of both events occurring.
Yes.
Okay.
Great.
All right.
So here we can say the question was asked, are the events independent? Are they independent?
Yes, they are.
Yes, they are.
Yes, they are.
So here we're just looking at a quick recap here. We would have done this on the board. So we're just running through to, you know, for those who are just joining.
So the history only would have been simplified to give us a third. French only would have been, okay, let's start from the top. 24 of those students, 20 of the students did history only, 20 out of the 60. 20/60th, simplified to give us a third of the students did history only. Then we looked at French. French, we have 24 out of the 60 students, simplified to give us 2/5 of the entire grade 10 students that did French and history. Then we had those students who the probability of those students doing history and French. Looking at the Venn diagram, you can see it clear as day. 8 students would have been those students that would have done history and French. Simplify 2/15. All right? So then we would look at now
we looked at this,
right,
and
the
they're good, man.
Yeah,
they're
man.
good. And
we
these
multiplied
two
them, we got the
events, as we said
250,
earlier,
are independent.
All
right.
So let's take a little bit closer look at probability of independent events. So we would have been doing independent events. We're looking at probability. So let's just put everything together. When two events A and B are independent, the probability of both occurring is the probability of A and B is equal to the probability of A multiplied by the probability of B.
All right.
Which we looked at earlier. And in going further, here we have it. Probability of A, and we use in our symbol intersect B equals probability of A times probability of B, which is known as the multiplication rule for independent events. And it is also known as the AND rule for independent events.
Yes.
So let's see if they're following. Let's look at another activity.
All right.
So a fair die is thrown twice. What is the probability that 2 5s are thrown?
Well,
so the fair die is thrown twice.
All right.
What is the probability?
Let's look at it before we even look at any solution. A fair die, why you call it a fair die, by the way?
Because it's fair.
It's balanced. There's no cheating in the die, right? So a fair die is thrown twice. So we throw it one time, we get 5. We throw it a second time, you plan to get 5?
Guess what? If we throw it a second time, it has nothing to do with us throwing it the first time.
Well, all right, okay. So what is the probability of 2 5s being thrown? So what's the probability of the first 5 coming?
Well, we have 6
How we
possible
know
outcomes.
the die have 6 possible outcomes? How
we
you
have
know
1,
that?
2, 3, 4, 5, 6.
Oh,
6
it's
faces.
a cube. It has 6 faces.
Yes,
there
we
you
learned
go.
cube earlier.
And 5 is only on one of the faces.
Yes.
Great.
So it's 1 favorable outcome out of the 6 possible outcomes.
So the first throw, the probability of getting the 5 is 1/6.
1/6, yes.
No, I'm throwing it a second time. The probability change. I'm sure it changes.
It's still going to be 1/6.
You sure?
The die doesn't change. It's this die.
All right.
6 faces.
So,
1, 2, 3, 4, 5, 6.
All right. So
Won't change.
it's the same 1/6 for the second.
Yes.
All right then. All right. So that means, and you did say independent events, I can multiply them. So that's 1/6 multiplied by 1/6. That's 1/12.
Really? You sure?
You sure? Oh, I think it's 136.
Okay.
Okay.
Nice. Good. So remember now,
All
it's
right.
6
So it's
times
one
6.
throw of the first 5.
1/6.
1/6. Second throw, it's
1/6.
and first 5 and second 5. And we
Yes.
have probability of 5 in the first throw, probability of second 5. And we will multiply 1/6 by 1/6, giving us 136.
All right. Let's look here now. So here we have 2 events occurring and they are independent. And we are told that the probability of event A
Is a third.
We're also told that the probability of event A and B occurring is 1/12. We're asked to find the probability of event B. Now we would have learned earlier
How to find that?
how to find all of this.
Yes. So what are we going to do?
But I'm just saying that we learned.
Okay, so we can form an equation there. We can form a math sentence. Let's use the term math sentence. So I can use the probability of A intersect B, or the probability of A occurring and B occurring is 1/12. So I also know that the probability of A and B is equal to the probability of A multiplied by the probability of B. So let me write that first.
Yes, let's write everything you would have just shared. So
A intersects
and B is the probability of A equals, yes, multiplied by the probability of B. And we
I know that is 1/12, so I can substitute that for 1/12.
Yes.
I know the probability of A is 1/3.
Good.
I can put a question mark there.
Well, we can leave it as probability of
That
B.
can work too. All right, so now I would like to find the probability of B.
So
what is being done to it? It's being multiplied by 1/3. So
what would we do? We're looking at a what here?
Divide by 1/3 or multiply by 3. I'm trying to make the probability of B the subject of my mathematical sentence there.
Great. So we're trying to do that with our equation.
So let me undo what's being done over there.
So we're going to multiply both sides by 3 of the equation by 3.
Right.
And when we simplify all this,
so I have the probability of B all by itself, and I get that to be 1/4.
Yes.
So let me check that now. Can I check that?
Yeah, man, you can check. I'm
so
sure we're right, man.
So that will be 1/4 multiplied by 1/3. 4 times 3, that's 12. That's 1/12.
So if we wanted to check, remember now the probability of A times the probability of B should give us what the probability of A and B is. So here we have probability of A was
1/3.
Yes.
And the probability of B is 1/4.
Is 1/4, which gives us 1/12.
And
here we have 1/12.
So with the fact that we know that both events were independent, we simply use the multiplication rule to solve for one of the unknown.
Yes, we did. Okay. We did. And here we have our solution right there. See, we're on the right track.
There you go.
So we're multiplying each side of the equation by 3, which gives us the probability of event B is 1/4. And again, what type of events are we looking at?
Independent events.
Great.
That means the occurrence of one does not affect the probability of the occurrence of the other.
So the probability of one event does not affect the probability of
the other event.
Great. Good job.
All right, activity 5.
Nice. Good one.
Sambod tosses a coin and then rolls a die. Why would he do that? What is the probability of him getting a head on the coin and a 4 on the die?
Well, you ask why he would do that.
Yeah,
Here he's telling you why he would do that, because he wants to know the probability of getting a head on the coin.
Okay.
And a 4 on the die.
Well, we spoke about the coin, and the coin only has 2 faces. It has a head and it has a tail. So the probability of getting a head, he wants a head, right? It's always 1 out of 2 occurrences.
Yes.
A half. Now the 4 on the die. We know that the die is a cube. It has 6 faces, and the numbers are not repeated on each face. So there's only one side containing 4. So it's 4, 1 side out of the 6 sides.
Great.
So the die is 1/6. So to get the 4, I should say, the probability of getting a 4 is 1/6. The probability of getting a head is a half.
All right. So you have 1/6 and a half. But question, what would you tell me about these events? If because he's going to toss the coin, he's going to roll a die. Will him rolling the die have any effect on him tossing a coin? What do you think? So he
absolutely not. Unless him have the 2 of them in them hand and it affect him somehow. But no, they're independent events. They are independent events. They do not have any bearings on the other result,
Great.
on the other probability.
Good. So let's see now. So you would have shared half
for the head,
coin,
right?
Okay, and you would have shared 1/6 for the die.
All right.
So let's check. So here, good job. So the probability of getting a head, a half. The probability of getting a 4, 1/6, and the probability of getting a head and a 4 on the die is a half multiplied by 1/6, which gives us 1/12.
Okay, so what we're saying, if he were to throw the die on the coin, it's 1/12 probability that he can get a head and a 4.
And for those who are joining, I hope they would have been learning, because we're looking at something interesting.
The multiplication rule is pretty cool.
Yes,
it helps you get your probability of 2 independent events occurring together. Pretty easy. Without drawing up, you know, that long table that you did?
Yes.
Yes.
Don't worry, we're going to look at a table when we come back as well.
Oh my goodness. We're going to our final break. When we come back, more CSEC math.
Hello, we're back to CSEC Math, where we have been discussing the probability of simple events. And here, we are going to be taking a look at our second to last activity for the day. But just reminding for those of us who are just joining, we're looking at the probabilities we would have shared earlier, simple events, and we went into independent events. So here goes. Simba tosses 2 coins. Use a table to find the probability that he gets a head on one coin and a tail on the other coin.
So since we're using a table, we're going to go right to the table to pretty much see what the table will look like.
What the table would look like.
Most definitely. So the options for tossing a coin, it's very simple. You can either get a head
or a tail. So this would have been coin 1.
Exactly.
Coin 2. All right. So on coin 1, here we are seeing
we could get a
head, and on coin 2, we could
also get a head.
All right. And if we have a tail on coin 1, we could have gotten a head on coin 2.
Exactly.
And here we have a head on coin 1, and then we have a tail on coin 2. We have a tail on coin 1 and a tail on coin 2. So how many possible outcomes are we seeing here?
Well, that looks like okay, since we are talking about the coins independently.
Yes.
Well, in that case, we have 4 possible outcomes.
Good.
Right. So let's just go from there. We have 4 possible outcomes. For the first coin here, we can either have a head or a tail, and we've combined it. For the next coin, we can have a head or a tail, and we've combined it.
Right.
So we have 4 possible outcomes because the coins are independent of each other.
All right, I'm going to ask a question. Hold on. Don't rejoice just yet. He wanted to know what is the probability of getting a head and then a tail.
Okay,
So look at the table and tell me.
if it's a head and then a tail, so he would have tossed one coin first, looked at the result, and then tossed another coin. He can only get it once.
You sure I'm seeing a tail and a head? Otherwise,
Yeah, but you see, I made sure I said, the coins, if they're independently tossed, right, and we're looking at coin one, so we colored the coins. One coin colored and one is not. The arrangement is going to be different.
all right.
So we would only have one out of four toss.
And they're independent
four
events too,
combination.
yes.
Yes.
So it's going to definitely be one out of our total outcomes here. Well, our total possible outcomes here, which is four. So it's a quarter. Great.
And he was specific, head and tail.
Yes, head
Not
and tail.
and head.
Good. So it's head and tail.
Right.
So
it's
both
1/4.
independent events, head and tail.
Yes.
All right. So then now, so we understand him tossing the coin. So we're going to be taking a look now at our last activity for today. So here we see, using the multiplication rule, we could have gotten half times half, which is a quarter.
Right.
So we're running straight into our activity.
And this is because he
cumulative
treated both coins as independent
Dependent
toss.
events, yes.
Okay, great.
So here goes.
Stella and Sadie were having a discussion on the different eye colors of the persons on a flight going to Florida. As the flight was delayed, they needed something to do. They wanted to find out the probability of sitting next to a female with brown eyes and a male with blue eyes.
You know, I think I need to do this one day too. You know, this looks fun.
It could be. An experiment was conducted and the findings were presented on a contingency table.
All right,
All
so
right, let's
we
look at
know
what
that
that looks
we're
like.
looking at black, we're looking at different colors, eyes, so they want...
Yes, eye colors.
Great, so we have to point out something here. They wanted to find out the probability of sitting next to a female with brown eyes
And a male.
and a male with blue eyes. So remember, a female with brown eyes and a male with blue eyes.
Okay.
So we have to remember that we're looking at the probability of those two events happening.
Okay.
All right. So let's look at the table.
So they would have drawn up this table, and this is what they would have found out. So they realized that the passengers, they had black eyes, which is very rare, brown eyes, blue eyes, green eyes, and gray eyes.
Contact
Then they
lens?
tallied. Yeah, well, we don't know. They really couldn't go up to people and ask them. So they recorded. There was 2 females with black eyes, 4 males with black, brown, 14
females, 6
and
males.
you can look at the array.
Yes,
But-
but we're asked a simple question.
Right. So we're asked to look at a female with what color eye?
Brown eyes.
All right, so
which
what is that?
14.
14.
So that would be 14.
Out of the entire passenger list with it, which is
56.
Then they wanted to look at a male with
blue eyes.
And that would have been 10
10
out
out
of the
our
same
56.
56. All right. So what's the probability? So we looked at females with brown eyes. We got
Yes.
that. Males. All right. Now we know that we have learned about the multiplication rule, right? Let us see if it stands here. So the probability of sitting next to a female with brown eyes
Yes.
and a male with blue eyes
eyes
is equal to the probability of sitting to a female with brown eyes,
Which is 14 out of
multiplied
56, yes.
by the probability of sitting next to a male with blue eyes,
which is 10 out of 56.
Let's
Great.
work that out.
And when we multiply it through, we have it right here.
We would have simplified best as
Yes.
possible. 1456 is a quarter and 1056 is 5/28. When we multiply, we would have changed them to decimal fractions, giving you 25 hundredths multiplied by 18 hundredths, giving us
45 thousandths.
There we go.
Great.
So that is the probability
of sitting
next to a female with brown eyes and a male with blue eyes. Now remember, the plane has 3 seats. They could sit in the middle or the other 2 persons could sit over there, but it's possible. That's the probability for them sitting
Yes,
beside that
out
combination.
of the 56
Because-
passengers that they would have looked at, done their
Right.
experiment, this would have been the probability.
Exactly.
And I think here this is good, you know.
Yeah.
It's very good that we can look at what is happening in every day and we can see probability taking
Most
place.
definitely.
So what's the probability of Tamika and Camille sitting
Next to a blue eye.
next to a blue eye and a brown eye. Maybe it could be similar. We would have to work that out.
Right. So we'd have to see how many blue eyes and brown eyes are around.
Yes.
All right. Take note. So we have independent events. The occurrence of one event has no effect on the probability of the occurrence of another event.
And if a particular outcome or event in one experiment does not affect the probability of outcomes or events in a second experiment, then the outcomes or events are said to be independent. And finally, we looked at the multiplication rule.
Yes.
When two events A and B are independent, the probability of both occurring is the probability of A and B gives us the probability of A multiplied by the probability of B, which we will see sometimes that this is also known as the multiplication rule for independent events. Sometimes we'll see that.
And we now show that, yes, we now show that the multiplication rule makes finding the probability of independent events much more efficient.
Yes.
It's an efficient way. Yes, we could draw up the table. We could definitely use a contingency table. But that would take some time if you have several different occurrences. But the multiplication rule does cut down the time.
It does. It does.
Awesome. All right.
I think they would have learned independent events today.
Yes.
Probability of independent events.
And?
Well, under the probability of independent events comes the multiplication rule.
Okay.
So they would have learned today.
And we did review experimental probability and theoretical probability. And clearly, you can have independent event in any such.
Yes.
All right, that's all for today. We hope you have a clear understanding of probability of simple events. If not, you can catch a rebroadcast of this lesson on JNN today at 5 p.m. Until next time, keep safe. Wash your hands regularly, please. Sanitize and do continue to wear your mask.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.